Okay, in this video we're going to explore 7 different ways to evaluate limits, and these are generally thought of, I would say this is a good easiest to hardest method. Of course, before you try any of the methods you should always use direct substitution. So I'm going to work through a couple examples of each. This video may be long, so you can skip ahead. I've labeled what type I'm working on if you're ever wanting to just jump and see one possible type. But I encourage you to watch the whole video to see all the different kinds. Okay, before we jump into evaluating limits, we should take note of some limit properties that we might have. If we have these conditions, the limit as x goes to a of a function exists, and we'll say it equals L, and the limit as x goes to a of a different function exists, and we'll say it goes to m. If both of these exist, then we can apply some limit properties. For example, if I wanted to know the limit as x goes to a of f plus g of x, I could take the limit of each of those separately, and it'd just be the limit of f, which is L, plus the limit of g, which is m. The next property would be just changing this plus sign to a minus sign. So I'm going to just write plus or minus right there. We also can multiply our function by a constant. So if I said the limit as x goes to a of a constant times a function, we can translate that constant to the outside and take the limit as x goes to a of our function f. And in this case, that would wind up being c times L. We also have the multiplication one. So if we're trying to find what is the limit as x goes to a of f of x times g of x, we can split that into the limit as x goes to a of f of x times the limit as x goes to a of g of x. So in this case we would get a value of L times m. Same thing goes for division. Let's shrink this up. Okay, division, if we asked about the limit as x goes to a of f of x divided by g of x, that is the same as asking about the limit as x goes to a of f of x all over the limit as x goes to a of g of x, which in our case would be L divided by m, provided that m doesn't equal 0. If it equals 0, there's other things that we need to take a look at. Finally, a less common one that we see occasionally is if we are asked what is the limit as x goes to a of f of x raised to some power. And in this case what we can do is we can move the limit inside, so we just are asking what is the limit as x goes to a of f of x, and we raise that answer to the power. So for us that would wind up being L raised to the power of p. Okay, let's jump into it. The first type of evaluating limits would be direct substitution. Okay, example 1 we'll call it. Perhaps I'm asked to find the limit as x goes to 3 of 2x squared minus 6x plus 1. Doing direct substitution is always the first thing you should try, and all it means is let's plug this value in for x. So we get 2 times 3 squared minus 6 times 3 plus 1, and that is equal to 9 times 2 is 18 minus 18 plus 1. So that limit evaluates to 1. Because we get a value, then we know that the value exists. And occasionally we'll get to things that are undefined, and we'll have to take a different approach. Taking a look at a second example, we'll just say the limit as x goes to pi of sine of 2x times x. So here we try direct substitution. We're going to plug pi in for any occurrence that we have x, and we get sine of 2 pi, and we take that quantity and we multiply it by pi. Sine of 2 pi we know is 0, and 0 times pi is equal to 0. So that's our answer. Direct substitution is definitely the first one we want to try, because if we can solve it with direct substitution, that's the easiest possible thing that we can do. However, not all limits can be solved with direct substitution. Okay, let's look at an example where direct substitution doesn't work. Let's say I wanted to take the limit as x goes to 3 of, we'll just say 1 over x minus 3 quantity squared. Now, in this case, if we were to do direct substitution, plugging a 3 in here, we get 1 over 0 squared, and this is not allowed. We can't divide by 0, so we are undefined. So that brings us to the next type of limits. Having an awareness of vertical asymptotes can help us solve problems of limits that are not working out for us. So going to this example, the limit as x goes to 3 of 1 over x minus 3 quantity squared. If I picture what this graph looks like, I know that 1 over x looks like this, so that's 1 over x. I know that 1 over x squared looks like this. And if we're going to change that to 1 over x minus 3 squared, what's happened is we shift it to the right 3 units, and now our vertical asymptote is at 3. And we get a curve which looks like this. And that awareness of the vertical asymptote allows us to kind of think about what is going on graphically. And as we approach from the left, we are going to go up to infinity, and if we approach from the right, we're going to go up to infinity. So since the left and the right both go to infinity, we know that this approaches infinity. So that's one that we can do just by being aware of vertical asymptotes. Let's take a look at another example. Okay, so what we could say is maybe we want to know about the limit as x goes to pi from the positive side of x divided by sine x. Well, our direct substitution fails us because what we get is pi over sine pi, and we know that sine pi is 0. And since we can't divide by 0, that doesn't work for us. So what we can do is we can think about what this might look like. And in this case, trying to visualize the graph is a little bit harder, but if we think about what's going on with just the graph of sine, as we approach, oops, I drew cosine. As we approach pi, right here, we are getting very close to the value of 0. And if we approach pi on this side, we're also getting very close to 0. So what's happening is, since we're talking about the right side, we are interested in what's going on here. And x over sine x, we are basically getting x divided by a negative number that is very, very, very close to 0. Or I guess now we've substituted pi in here. So a number divided by an almost 0 number is going to get very, very large. So this approaches infinity, and since we're going on the right side, we want to consider that negative. So the answer to this one is negative infinity. So we thought less about it graphically and more about what was going on with just the denominator. So thinking about the graph of part of the function or all of the function will help us tackle this. Another case that we might encounter is with a piecewise function. And basically with a piecewise function, you're going to have some function defined at two different pieces. And if you're interested in evaluating it, you're going to have to consider which piece we're talking about, or maybe we're talking about the spot where it jumps. So like if x is less than 2, if x is greater than or equal to 2, you're going to consider right at the jumping point. So you'll have to look at both functions. So let's see what this plays out like. Okay, so we have a piecewise function here defined x squared minus 2x plus 1 if x is less than 2. And if x is greater than 2, then we have a trig value of cosine of x minus 2. If you're being asked to find the limit of f of x as x approaches 2, we notice that that's the point where we break between the two functions, and so we're really going to need to find both the left-hand limit and the right-hand limit. So if we split it up and we get the same value, then we know the value of the limit. So taking the left-hand limit is going to, we'll try direct substitution. We get 2 squared minus 2 times 2 plus 1. That's 4 minus 4 plus 1 is 1. So our left-hand limit is 1. And then we try the right-hand limit and we get cosine. We'll try direct substitution. Cosine of 2 minus 2 is cosine of 0. And we know cosine of 0 is 1. Because these values of the piecewise function equal one another, then we can say that the limit is 1. Or because they both equal 1. If they disagreed with one another, you would say the limit does not exist. I don't really want to show another example of the piecewise functions because really what it comes down to is you're just going to evaluate the limit for each one of them separately. And so I want to explore more about how to evaluate other types of functions. Keep in mind if I asked what the limit is when we go like x to 1, well, or we'll say, I'll write it down here, the limit as x goes to 5 of f of x, the only function we need to plug it into is the bottom piece of that function, and we'd find that that gives us an answer of cosine of 3. Okay, let's take a look at another type. More often than not, if you're finding a limit where something doesn't work out, like we had the 1 over x minus 3 example, as the limit went to 3 on this one. More often than not, when it doesn't work out, if you get something odd going on, you're going to need to do some sort of algebra. And the next example will show you the most basic kinds of occurrences of this. So I've kind of called it some basic algebra. Let's say we're asked to find the limit as x goes to 1 of x squared minus 1 over x minus 1. Now, first, of course, we'll try direct substitution, and we get 1 minus 1 over 1 minus 1, which is 0 over 0, and we're not allowed to divide by 0, so we can't do that. So what we're going to do is we're going to try some basic algebra, and I say divide out, because oftentimes what happens is we have a fraction, and there's something that divides out. So if we factor our numerator factors to x plus 1 over x, or x minus 1 times x plus 1, and our denominator stays as x minus 1. And we see that a term divides out, and we are now able to do direct substitution because a term divided out. So the limit as x goes to 1 of x plus 1. Direct substitution tells us that that is equal to 1 plus 1, which is 2. So our limit approaches 2. Graphically, for the curious, what this winds up looking like is what we have is a line through x plus 1, so there's our x plus 1, and then at a value of 2, we wind up having a hole in the graph. So that's what it looks like visually. Let's take a look at another example of this. maybe what we want to do is the limit as x goes to 2 of x squared minus 3x minus plus 2. And on the bottom we're going to do x squared minus 6x plus 8. So again, we could try direct substitution, and we would get 4 minus 6 plus 2. 4 minus 6 is negative 2 plus 2. 0 over 4 minus 12 plus 8, 0 over 0. So the direct substitution doesn't work for us, so we will try factoring the numerator and denominator. And the numerator factors to x minus 2 times x minus 1, and the denominator factors to x minus 2 times x minus 4. And we see that the term now cancels, and we can try direct substitution now that the term cancels. So if we plug 2 into the top, we'll get a 1, and if we plug 2 in the bottom, we'll get a negative 2. So our answer is negative 1/2. The limit approaches negative 1/2. Okay, so sometimes our basic algebra of factoring and canceling doesn't work for us, and we might have something that doesn't look like it can be factored. So maybe like 1 plus 4, or 1 over 4 divided by, I can't speak, 1 over 4 plus 1 over x times divided by 4 plus x. And this one, no factoring really looks like can happen there. So we might need some more intermediate algebra. So let's look at that in the next one. The limit as x goes to 4 of 1 over 4 plus 1 over x divided by 4 plus x. And we substitute 4 in because we always try direct substitution. We get 1 over 4 plus 1 over 4 all over 4 plus 4. 1/4 and 1/4 is 1/2. Divided by 8 is 1/16. And lo and behold, we find direct substitution works for us, and so we don't need to do anything difficult. And that kind of tells us an important lesson. Oftentimes people jump in to trying a difficult procedure before they try direct substitution. So don't just immediately assume that it's going to be a difficult process, because sometimes we get easy processes. So let's try another one like this. Maybe the limit as x goes to 0 of 1 over 2 plus x minus 1 over 2 all over x. Here what we've got is something where if we did plug 0 in, we'd have 1/2 minus 1/2, which is 0 in the numerator, and we have 0 in the denominator. So direct substitution fails us, and we need to handle this with a different trick. So what we can do is we can simplify this all out. There's different approaches to cleaning this all up. What I'm going to do is create all fractions with a common denominator. So the first fraction I'll multiply top and bottom by 2 to create a common denominator. The second fraction I will multiply top and bottom by 2 plus x to create a common denominator, and all of this is over x. Then if we start to simplify this down, we're going to get 2 minus 2 minus x. So the numerator simplifies to negative x over 2 times 2 plus x, and the denominator stays as x. And we know that when we are dividing a fraction by a fraction, let's toss this up here, we can write the numerator times the reciprocal of the denominator. And at this point, we see that we have some x's which cancel out. And now let's ask ourselves back what we're doing. We're trying to find the limit as x goes to 0. We've used least common multiples or least common denominators to rewrite the expression like this. And now let's try direct substitution. If we plug 0 in, we are going to get negative 1/4 as an answer. So using least common multiples or least common denominators, kind of a little bit more advanced algebra, but not too difficult. I want to look at one more example like this, where we're going to use some of this intermediate algebra. Let's do the limit as x goes to 0 of 1 over x minus 1 over x squared plus x. If we plug 0 into this, we're going to get 1 over 0 minus 1 over 0, and that doesn't work out for us. So let's see what we can do to combine these fractions and maybe get something that works. My first fraction has a denominator of x. My second fraction has a denominator of x times x plus 1, if you factor it. So I can see right away that what I need to do is multiply my first fraction by x plus 1 so that I have a common denominator. Here we have x times x plus 1. So there's my first fraction, and to that we are going to subtract my second fraction. And when we simplify the numerator, we wind up getting x plus 1 minus 1, which is just x, and the denominator stays as x over x plus 1. And we see now that a term can cancel, and we're left with just a 1 in the numerator. And at this point, we can evaluate the limit by direct substitution. Plug the 0 in, and we get an answer of 1. Okay, moving forward, we're going to take a look at one which requires a little more advanced algebra. So I'm calling this the advanced algebra option, and it usually involves a radical symbol and rationalizing the conjugate. So real quick, a reminder, a conjugate, if I had like 5 plus the square root of 3, the conjugate to that would be 5 minus the square root of 3. So all that happens is we change the sign of the radical to find the conjugate. And we'll see what that does for us in the next example. Okay, let's say we're saying the limit as x goes to 9 of the square root of x minus 3 over 3 minus x. Okay, what we have here is, and what really clues me in, is the fact that there's a square root. So right away, of course, I'm going to try direct substitution, and direct substitution gives me 3 minus 3 over 3 minus 9, and lo and behold, that actually is an answer, 0 over negative 6, which is 0. Boom, we're done. Direct substitution works for us. Don't forget, direct substitution works some of the time. So, an example that looks very similar, where direct substitution won't work, is, let's do the limit as x goes to 4, we'll say square root of x minus 2 over 4 minus x. Now if we try direct substitution, we would get 0 over 0, and that's not allowed, so we need to do something to make this possible. And that's what rationalizing the conjugate is, or using a rationalization conjugate. Because I have the radical, I'm going to be tipped off to the fact that this might be a useful trick. So what we do is we take our function, and we're going to multiply the top and bottom by the conjugate. So do root x plus 2, root x plus 2, and the limit should always travel with us. And when we distribute in the numerator, what we get is, limit as x goes to 4, the root x times root x is x, and then we have plus 2 root x minus 2 root x minus 4. We have x minus 4 over 4 minus x. And at this point, we can try direct substitution. If we plug 4 in, we're going to get 0 over 0. And again, that doesn't work out for us, so we need to do some more work. And that's kind of why I'm calling this advanced algebra, because oftentimes it takes multiple steps. So what we can do is we can say the limit as x goes to 4. I noticed that the top and bottom look very similar. I'm going to write the top as x minus 4, and the bottom I will write as negative x minus 4. Because that really is what it is. If you factor out a negative, you wind up getting the same thing. And now I see, because of that, the terms cancel, and I get an answer of negative 1. There we have it. So let's take a look at another one requiring rationalizing the conjugate, because I think this is the most difficult one and worthy of looking at another example. So what we have is the limit as x goes to 2 of 4x plus 1 minus 3 over x minus 2. And when I look at direct substitution, I see that that puts a 2 in the denominator, and the 2 minus 2 gives us a 0, and so we're going to get something that's undefined. So direct substitution fails us, and then I'm going to try some algebra on it, throw some algebra at it. I recognize the radical, so I think maybe I should try rationalizing with a conjugate. So I multiply the top and bottom by the conjugate. So again, what you can do is you can just change the sign that connects them. The minus became a plus. You can also think of it by leaving it the same and changing the sign of the radical. But as long as one of the two pieces has their sign change, it should work out for you. And 4x, or root 4x plus 1, when we distribute this all out using our foiling techniques, we're going to get 4x plus 1 minus 9 over x minus 2 root 4x plus 1 plus 3. And our numerator becomes 4x minus 8. And we're still not where we can substitute in, because we still have that 0 that would happen right there. So then our numerator factors to 4 times x minus 2. And now that x minus 2 cancels out, and we are stuck, we're not stuck, we arrive at the limit as x goes to 2 of 4 over root 4x plus 1 plus 3. And at this point we can try direct substitution, and we wind up getting the answer of 4 over the square root of 5 plus 3. There's our answer. If you're being really tedious, most mathematicians don't like the radical in the denominator, so we would use another conjugate to remove that radical. Alright, so when all else fails, when you're doing these problems and none of these tricks are working, you're going to throw a sledgehammer at it. Basically beat it with some math and see if anything happens. So sledgehammering it is really useful if none of them work, and I'm going to show you this in the next example. Usually this is a last resort because it can get a little bit long. So let's try one example in that category. Okay, here we have a fairly innocent looking problem. However, if we do plug 0 into it, we find that what we would have is x to the third minus x to the third over 0, which is 0 over 0. And that doesn't work. I don't see a square root symbol, so I can't rationalize the conjugate. I don't see any fractions, so I can't combine fractions. There might be a way to do some factoring and trying that path, but really I think the best track is to let's expand the top all out and see what cancels out and basically throw some math at it. So first off, the top will become x plus h times x plus h times x plus h minus x cubed all over h. If we combine our second two, what we would end up having is x plus h times x squared plus 2xh plus h squared minus x cubed, and this is all over h. Then we would factor in that x plus h again, and we would have x to the third plus 2x squared h plus x h squared plus hx squared plus 2x h squared plus h to the third minus x to the third, and this is all over h. And now I can start to see why this is kind of a last resort. There's a lot going on in here. We could start combining and canceling terms. First off, x cubed cancels with x cubed. Then I'm going to combine my x squared h terms, 2x squared h and hx squared, so that's 3x squared h, and then my xh squared and xh squared gives me 3xh squared, and then we're left with an h cubed. This is all over h. Still kind of tracking all of our algebra along the way. At this point, I see that all three terms have an h, and I can factor the h out of my numerator. 3x squared plus 3xh plus h squared. And in factoring that h out, the h cancels, and we're able to do this now. We can take the limit as h goes to 0. We plug 0 in for h, and we find that both of these terms go to 0, and we get an answer of 3x squared. Whew. That one was a little bit hard. The cool thing about this is oftentimes it comes in a very similar form. That similar form, there's oftentimes you're taking the limit as h goes to 0 with just an h in the denominator. Somewhere in there there's a x plus h. And all of this is stuff which connects to calculus concepts later on and the definition of the derivative. So a lot of times they're hinting at, hey, this is the derivative for the people who know derivatives. And the people who know derivatives might recognize that really we're just asking, what is the derivative of x cubed? And if you know derivatives, then you know that is 3x squared. If you don't know derivatives, this doesn't help you. But if you do, awesome. Okay, I suggest you take a look at various problem sets for limits and work through a lot of these. Calculus A-B students, the limits is a bigger deal on the test than it is for Calculus B-C students, but I think anybody would benefit from practicing their limit rules because the limits come back throughout the year and a lot of things are defined with limits. Anyways, just wanted to throw that out there. That's my 2 cents, and I hope you enjoyed this video.